Hello viewers, how are you? Welcome to my channel Physics with Rams. So today we are going to discuss about a specific heat as well as we are going to discuss about a Mayo's formula. So before going to start this topic, those who are new to my channel, please subscribe my channel so that you can receive notifications regarding my channel as well as you can watch my previous videos so that you can clear your concepts and you can achieve your target. Either it might be JE or it might be neet. Let's start this topic. Specific heat. So when we consider the specific heat, it is being represented with the C. For this, let us consider a system. A system can be a gas or a liquid or a solid body. When we heat this system, the heat energy is being transferred to the system so that molecules gain the energy. Then, as the molecules gain the energy, their temperature rises. So, the specific heat is being represented as a C equals to amount of heat transferred by mass of the substance into increase in the temperature. Increase in the temperature or decrease in the temperature. So now when we remove the heat from the system, then we can represent it as a decrease in the heat. So from this heat here we can represent that delta Q is equal to mass into specific heat into change in the temperature, delta T. Now observe that here we can define this specific heat as a amount of heat required by 1 gram of substance. To raise its temperature by 1 degree Celsius is known as a specific heat. So here the specific heat is being considered when the same system remains. Means if you consider water, so here when the heat is being given to the water molecules such that its temperature rises, then we can represent it with as a specific heat. Suppose if the liquid converts into vapor on heating or on removing the heat, if the liquid converts into solid, then we represent it as latent heat. So after that, when the same state remains, we represent the condition in terms of specific heat. When the state changes for the particular body, then we can represent it with the latent heat. Whereas we know that the latent heat is being defined as amount of heat required by a substance to change its state at constant temperature. At constant temperature is known as latent heat. So now based on that we are going to discuss about heat capacity. Whereas heat capacity is being represented with H, and it has been defined as amount of heat required by a substance to raise its temperature by 1 degree Celsius is known as heat capacity. Observe that the specific heat is being given as a C equals to delta Q by M into delta T. Whereas the heat capacity is being given as H equals to delta Q by delta T. So the relation between specific heat and heat capacity is given as C equals to H by M, where H is heat capacity, C is specific heat. Take a screenshot, we will continue. Okay, as we had represented that specific heat is being given as C equals to delta Q by M into delta T. Now, let us consider that work has been done on this system. So now, when we consider this, here we are compressing the gas. We can represent that the gas system has been compressed or the gas has been compressed. When it has been compressed, it has been compressed. Observe that volume decreases. As the volume decreases, we know that pressure is inversely proportional to volume. So, as the volume decreases, pressure increases. And we know that pressure is directly proportional to temperature. Thereby, the temperature increases. So, here observe that the amount of heat supplied in this condition is 0. If we consider it is 0, here delta Q is equal to 0. Whereas according to this equation, observe that delta Q is equal to M into C into delta T. Whereas the temperature has been raised, but still we can represent that the specific heat will be 0. Why? Because the amount of heat supplied to the system is 0. Whereas when let us consider that the gas has been expanded. In the case of expansion, we can consider different conditions. The first condition is the amount of heat supplied to the system such that its temperature increases. Temperature increases. Then the specific heat can be represented with a positive sign. Because here we can represent that delta T equals to final temperature minus initial temperature. As the final temperature is greater than initial temperature, we can represent that the specific heat will be positive. Similarly, when the gas has been expanded, whereas the temperature has been fallen, means the temperature decreases. If the temperature decreases, then we can represent that the specific heat is negative. Whereas if we consider that there is no change in temperature in the case of expansion, then the specific heat will be infinity. In this way, we can represent the specific heat in different conditions. So here the sign of the specific heat is being represented by considering the compression or expansion of different gases. So now, as we had represented this, observe that when we consider a gas in terms of moles, then the specific heat is being represented as C equals to delta Q by mu into delta T, where mu represents a number of moles for a gas. Here, in the case of gases, we consider two types of specific heats. Specific heat at a constant pressure, as well as a specific heat at a constant volume. constant volume. So now when we consider these two conditions in the case of gases by considering number of moles, when we consider this specific heat at constant pressure, observe that the pressure has been kept to constant whereas the volume of the body has been changed. Let us consider the initial volume of the system is V1 whereas the final volume is V2. Observe that here we had represented that V2 is greater than V1. Then volume has been increased. As we observe this condition here, we can represent that the amount of heat supplied to the system has been utilized by the gas molecules to increase its internal energy as well as to do external work. Just like if you consider a milk in a vessel, but if we close the lid and heat the milk, after some time the lid will be thrown away. Based on that, we can represent that the amount of heat supplied to the system at constant pressure is utilized to increase its internal energy as well as to do external work. Whereas the internal energy for a system is being given as delta U equals summation of kinetic energy plus the summation of potential energy. So the internal kinetic energy of the molecules as well as the internal potential energy of the gas molecules represents the internal energy for a system when we consider a gas. After that, similarly, when we consider the specific heat at constant volume, here the pressure of the system has been changed. Whereas if we consider the initial pressure as P1 and the final pressure as P2, then as the pressure changes, we can represent the specific heat where it is being given as C equals to delta Q by mu into delta T. As you know that pressure is directly proportional to temperature. With respect to change in the pressure, temperature changes. Whereas in this condition, only internal energy changes. At constant pressure, internal energy of a system changes. Whereas in the case of a specific heat at constant pressure, the amount of heat supplied to the system is utilized to increase its internal energy as well as to do external work. So completely in this case, the amount of heat supplied is utilized to increase its internal energy itself. So now observe that we had represented the conditions for a gas molecule at constant pressure as well as at a constant volume. So when we consider the first of thermodynamics, here we had represented that delta Q equals to delta U plus delta W. So here when we know that the work done is being represented as a delta W equals to P into delta V. According to ideal gas equation, we know that PV is equals to NR or mu R into delta T. Mu R T. So if we keep the pressure constant, P into delta V equals mu R into delta T. Let's substitute this values in this equation as we observe that delta Q is equals to delta U plus mu R into delta T. So here let us observe this. When we consider the specific heat expression, observe that specific heat at a constant pressure is being represented as a C suffix P equals delta Q by mu into delta T. Similarly, we had represented that at constant volume, pressure changes. When the pressure changes, the specific heat at constant volume is given as delta Q by mu into delta T. Or since delta Q has been considered as a delta U, we can represent it as a delta U by mu into delta T. Okay, now we are going to take a mu delta T as common. When we take a mu into delta T as common, observe that delta U by mu into delta T plus R. So let's bring this mu into delta T towards this side. Then we can represent it as delta Q by mu into delta T is equals to delta U by mu into delta T plus R. Observe that specific heat at constant pressure equals to delta Q by mu into delta T. Specific heat at constant volume is delta U by mu into delta T. So when we substitute here, Cp is equal to C suffix P plus R, or we can represent it as C suffix P minus C suffix V equals to R, which represents the Mayer's formula. C suffix P minus C suffix V equals to R represents the Mayer's formula. After that, in the case of specific heat at constant pressure, the amount of heat supplied to a system is utilized to increase its internal energy as well as to do external work. As well as in the case of specific heat at constant volume, the amount of heat supplied to a system is completely utilized to increase its internal energy. Based on that, we can represent that specific heat at a constant pressure is greater than specific heat at a constant volume. Based on that, we can represent that gamma, which is an adiabatic constant, is represented as gamma equals C suffix P by C suffix V. Take a screenshot, we'll continue. So, as we had represented that C suffix P minus C suffix V equals to R, as well as gamma equals C suffix P by C suffix V. So based on that, we can represent that as specific heat at constant pressure equals to gamma into C suffix V, where gamma is an adiabatic constant. Whereas when we substitute this in this equation, observe that gamma into C suffix V minus C suffix V equals to R. When we take C suffix V as common, we can represent it as C suffix V into gamma minus 1 equals to R. Then C suffix V equals to R by gamma minus 1. Similarly, when we substitute this value in this equation, we can represent that specific heat at constant pressure equals to gamma R by gamma minus 1. Take a screenshot, we'll continue. Let's solve a numerical based on this concept. Observe that a gaseous mixture enclosed in a vessel contains 1 gram mole of a gas with gamma equals to 5/3 and some amount of gas B with gamma equals to 7/5 at a temperature T. Temperature remains the same for both the gases. So now the gases A and B do not react with each other, then and assumed to be ideal. Now we have to find out the number of gram moles of gas B if gamma for the mixture is 19/30. So here we know that specific heat at constant volume is being represented as C suffix V equals R by gamma minus 1. So now initially for the gas A, gamma has been represented as 5/3. When we substitute here, we get 3R by 2. Similarly, when we consider gas B, the value of gamma for B is 7/5. When we substitute here, we will get 5R by 2. Whereas gamma for the mixture is 19/30. When we substitute in this equation, here we got 13R by 6. So now let's observe the equation for mixture. Specific heat at constant volume of the mixture is equal to N1 into C suffix V1 plus N2 into C suffix V2 by N1 plus N2. Whereas number of moles for the first gas is 1. So when we substitute all the values, observe that 13R by 6 equals to 1 into C suffix V1 is 3R by 2 plus N2 into 5R by 2 by 1 plus N2. Observe that here we can take R by 2 as common from these two terms. So here R as well as R gets cancelled and 2 gets cancelled, so we get a 3. Also that 13 by 3 is equal to 3R plus 5N2 by 1 plus N2. Let's cross multiply this equation. Observe that 13 plus 13N2 is equal to 3 into 3 is 9, 5 into 3 is 15N2. Let's send this 9 towards this and bring this 13 towards this. So other that 13 minus 9 is equal to 15N2 minus 13N2. So here 15 minus 13 is 2. 13 minus 9 is 4. 4 equals to 2 n2. So 2 to the 4. So we get n2 is equals to 2. So based on that we can represent that number of moles of the second gas is 2. Take a screenshot. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.